We're going to derive the integral test. We're going to start with the function y equals f of x, which is continuous, positive, and decreasing for all x values from 1 to infinity. We're going to create the infinite sequence a sub n as n goes from 1 to infinity, and that's going to be created because f of n will just be the f of x value when n is 1, 2, 3, at all the positive integers. This is what it would look like. If this was 1, this right here would be a sub 1. If x is 2, n is 2, this is a sub 2. And we keep doing this for all the positive integers. And this will go on indefinitely toward infinity. We're going to look at, let's assume in this case that I'm looking at the integral from 1 to infinity of f of x dx. And for our first case, let's assume that that integral is divergent. Based on that, I am now going to create circumscribed rectangles. Looking at this, we can see that the width here, the delta x everywhere, is 1. So my first rectangle is up a1 over 1. My second rectangle goes up a2 over 1. My second up a3 over 1. Then up a4 over 1. I keep doing this continually. What I've created are circumscribed rectangles. The area of this first rectangle becomes, the height is a1 and the width is 1, so that area is a1. So we can call that area a1. The area of the second rectangle is a2 times 1, a2. The area of the third, a3 times 1, etc. So we will now have created, going toward infinity, infinitely many areas of rectangles. And we can say that the areas are a1 plus a2 plus a3 plus a4, and this will go on indefinitely. And I can write that as series n goes from 1 to infinity a sub n. Because these rectangles are circumscribed, the sum of those areas will be greater than the area under the curve. This integral from 1 to infinity f of x is the area under the curve from 1 going on to infinity, and I've assumed it's divergent, but I now have summed up infinitely many circumscribed rectangles. Each of their areas will be, when you sum them up, will be larger than the area under the curve. So therefore we know that both the series and the integral will both diverge. So both the series a sub n and the integral 1 to infinity f of x dx, they both diverge. We're going to do the second example. Let's suppose that the integral from 1 to infinity f of x dx, the area under the curve, will assume it's convergent. I'm going to create a different picture for this. We're going to have y and x we're going to have the function again, y equals f of x is continuous and decreasing from 1 to infinity. From this we get the sequence that's infinite, a sub n, where f of n is f of x, n being 1, 2, 3, and goes on and on. But now we're going to create other rectangles. So when x is 1, we're here. When x is 2, when x is 3, 4, and we can continue like this indefinitely. Because the area under the curve is convergent, that means it's finite, I'm going to create my first rectangle will go up a2 over 1, my second a3 over 1, my next a4 over 1. So the area of my first rectangle is a sub 2 times 1, a sub 3 times 1, a sub 4 times 1. I now have, if I add up all these inscribed rectangles, I get a2 plus a3 plus a4 plus a5. It's just going to go on and on indefinitely. And that can be written as the series as n goes not from 1 but from 2 to infinity a sub n. Looking at this, we know that the sum of these areas, the sum of the areas is less than the area under the curve. And of course, it's the unbounded region from 1 to infinity. So we know that's less. So because the area under the curve is finite, since we assume convergence, this sum is finite. So to get the a1 in there, all I have to do is add a1, and a1 plus a finite is still going to be finite. So we have just shown that if the area under the curve, which is this improper integral, is convergent, then the series is also convergent. So both the series a sub n and the improper integral f of x 1 to infinity are convergent. So both the series and the improper integrals in both cases act the same way. That's what we call the integral test. Both the series are convergent, or in the first example, both are divergent. Let's go on to the next page and I'll show you an example of how we would do this. As my example, we're going to look at, you'll be given the series, n goes from 1 to infinity, some series. So let's say we are looking at the series n e to the negative n. It's not geometric, it's not telescoping, so it's not a series that we would have an actual finite value for. But we can decide, does it converge or does it diverge? So to do this, we're going to compare it to the improper integral 1 to infinity. Everywhere we have n, we put x. So x e to the negative x dx. We are going to look at that improper integral. If it converges, then we know our series converges. If it diverges, then our series diverges. To do the improper integral from 1 to infinity x e to the negative x dx, we are looking at the limit as b approaches positive infinity, 1 to b, x e to the negative x dx. But this is going to be an integration by parts, and I'm going to do a little shortcut on the side to do that. So my shortcut is I take my derivative column, my integral column. I have x, the derivative of x is 1, the derivative is 0. I have e to the negative x, negative e to the negative x, positive e to the negative x. And then it's plus minus. So the antiderivative becomes plus x times negative e to the x. So negative x e to the negative x minus 1 times that, minus e to the negative x. So that's just e to the negative x. I can factor out a negative x plus 1. So that will be my antiderivative. So this becomes limit b approaches infinity, negative e to the negative x, x plus 1, evaluated from 1 to b. And working through all the steps, we get limit b approaches infinity, negative e to the negative b, b plus 1, minus, plugging in 1, negative e to the negative 1. 1 and 1 is 2. And now working this through, since b is positive infinity, I like that because now I can put e to the negative b below. This becomes limit b approaches infinity, b plus 1 with a negative in front. I'll keep the negative there. And over e to the b plus 2 over e. And now, of course, we're going to do L'Hopital's rule for this. This is infinity over infinity. So by L'Hopital's rule, we're looking at the derivative of negative b plus 1 is negative 1 e to the b. Negative 1 over infinity, that just becomes 0. So our final answer is 2 over e. Because that's finite, that means it converges. So therefore, my original series, n e to the negative n, also converges.